Good afternoon, everyone. Thank you for joining us this afternoon. And thank you for joining the NIDDK Central Repository Data Science and Meet the Expert webinar series. This is our third session. If you're joining us for the first time, I encourage you to visit our website for more about the series and to replay past sessions and to register for future new ones. Next slide. The Central Repository Program is here to facilitate the sharing of resources generated by the NIDDK-funded clinical research consortia with the broader scientific community, and we have been doing this for more than 20 years, empowering countless researchers to test new hypotheses without the need to collect new resources. And we look for new and innovative approaches to promote the scientific utility and utilization and the impact of the resources we hold, including this webinar series. But also we are among a handful of NIH repositories that are Core Trust Seal certified, which indicates that we meet a specific set of standards, adding more value to our processes and our collections. Next slide. As you know, or you can imagine, we are part of the broader NIDDK data sharing ecosystem, and we're key to NIH's fairness and trustworthiness goals. We house a broad range of resources and provide linkages to resources stored outside the central repository. This helps us support our users in achieving their multimodal research aims. Next slide. Coming soon, we will have a new analytics workspace functionality. This cloud-based analytics environment will allow clinical researchers and data scientists to access a suite of integrated analytic tools and cloud computing resources in a user-friendly, secured workspace that will facilitate collaboration while minimizing data movement. It will also enable them to participate in and conduct data challenges to drive AI innovation, potentially streamline the data science lifecycle, and facilitate the discovery of AI-driven biomedical insights. Next slide. Speaking of data challenges, this webinar series is part of our broader data-centric challenge series, which will launch in the fall of 2023. The Data Challenge series aims to develop tools, approaches, models, and methods to increase the interoperability and usability of data for AI and ML applications. They were designed to build on one another, where each of the challenges and the challenge participants are tasked with developing innovative approaches for augmenting and enhancing the existing resources and the existing data in our repository, improving their utility for future secondary research. I encourage you to visit our website for information on our past and potentially future data challenges and to join our data-centric movement. Next slide. About this webinar series, this series serves to prepare potential challenge participants for future data challenges and to educate the next generation of data scientists. As a reminder, these sessions are held on the last Thursday of every month, and I hope that you continue to join us every month. And for more information on the webinar series, past recordings, and to register for future events, please, I encourage you to visit our website. Next slide. I will not take more time, so I will introduce you to our expert for the day. You have met her before, is Erika Christensen. She joins us from Booz Allen Hamilton. She holds a bachelor's degree in industrial and systems engineering from the University of San Diego. Her expertise lies in natural language processing and supervised machine learning. She has contributed to the RAVEN project at the Naval Information Warfare Systems Command. She currently assists the Chief Digital Artificial Intelligence Office, where she develops dashboards and data pipelines to assess risk and resilience for sailors at both individual and unit levels. Moreover, she heads the Data Science Learning Program from the Naval Information Warfare Systems Command to deliver training across the Navy in data science, machine learning, and artificial intelligence techniques. So I will leave it to you, Erica.
Beautiful. Thank you so much. I will take over screen sharing and we will get started with our session of today, which is AI Fundamentals Part 2. So over the past 3 months, we have covered the data science process. Then we dove into what AI was and how you can build out an AI organization. What are some key components of creating an AI project? And now we are going to look at AI applications. For training guidance on Teams, not on Zoom. We will have time for a Q&A, but feel free to put your questions in the chat as we go through class. We'll have some time with breaks throughout the class, and if I catch them during class, I will try to answer them in those individual sections, but we'll definitely have some time at the end for questions. Mentioned before, my name is Erica. I taught the data science process for the first session a few months ago, and I'm excited to be back today to take you through AI applications. This course was taken from the NAVOR's Data Science Learning Program. We have a hub of 10 or so courses and mini lunch and learns that we deliver very similar to these on various topics, and we'll be looking into our AI fundamentals course. We kind of pieced it over the past 2 sessions. So we'll be going over part 2 today, inspired by the NAVOR's Data Science Learning Program. This is what our agenda looks like today. So we're going to start with the statistics primer. It is the core functionality. It's really what AI was built off of. So taking a minute to understand our basic statistics and what kind of information they'll give us. And then we'll go into model metrics. How are we measuring? What are some key metrics for both classification and regression problems? And then we'll look at all of the fun stuff, the neural networks and their different applications, where we see them in the real world, and what is their usefulness. So first, jumping into our statistics primer. So these are, let me move this. You guys are looking at the teams. So these concepts are foundational to our conversation around machine learning. We want to start by covering some basic concepts and terminology. So this really includes exploring the common measures of central tendency, things like mean and median and mode, as well as the concepts of statistical distribution. And then we'll talk about how descriptive statistics are leveraged to describe or summarize quantitative variables. And then we'll also look at correlation and how it quantifies how strongly 2 variables are related to one another. To motivate this discussion, we will be using the same kidney data set that we've used in the past couple of sessions. So essentially, this is looking at kidney disease, and it has a number of descriptive variables around it if said patient has kidney disease, and then what their other numerical or quantitative values are for that. This is an open source data source, and it's listed on the UC Irvine Machine Learning Repository. This is a background of our data set here. So we have a lot of variables in there like age, their potassium, their packed cell volume, what their appetite was, what their blood pressure is. So it's always great to have a data dictionary, especially when you're dealing with complex data sets. You may have one, or you may have to create one as you're working through the data set and working through with yourself or subject matter expert on that data. It's a great reference point to make sure that you have it and that everyone on your team has the same understanding of the data that you're working with. Okay, here are the basics, the mean, median, mode distribution. They are basic, but they are very important because they help tell your story about the data that you're working with. So we'll look at descriptive statistics and correlation. So what are measures of central tendency? The purpose of these measures are to try and quantify the central value of a data set's distribution. So another way of saying this is that these statistics provide a numeric value around which the data tends to cluster. So generally speaking, these measures are fairly simple to calculate, and they also provide users with a lot of important information about this data. In practice, their application can allow data scientists to perform certain analyses quickly, like comparing data sets and identifying trends over time. We'll explore three measures of central tendency: mean, median, and mode. These are great even if you're going into more complex topics like machine learning or deep learning, which we'll touch on at the latter half of today's course. It's always great to start with your basic statistics. What are the descriptive stats of your data set? What does it look like? And this is a helpful comparison point, especially when you're bringing in multiple statistics or multiple data sets or comparing them from different time periods. So for example, this is our packed cell volume distribution based on, or packed cell distribution. So we can see that we have the majority of our data set is in the 40 to 45 range. Okay, so first looking at our mean. This is a concept you probably are all familiar with. This is the average of a given data set, which is calculated by summing together all of the values and then dividing it by the total number of values. So one way to imagine this is to picture the position of the fulcrum, like you see on this picture of the seesaw here, the mean representing the point of balance in a data set. So just like the seesaw, means are sensitive to outliers. The presence of an extreme value will have a significant effect on the mean. So we can look at this a bit more here in our example in our data set. So the values in this table below are from the kidney disease and show the packed cell volume for a sample of 9 different patients. So let's calculate the mean for this data sample. And I'll actually see if we can throw in chat here, if we can calculate what the mean is. So I'll give a few moments here. If you guys can calculate the mean and throw it in chat, what you think the answer is. Instead of employee, these are our 9 different patients. And the values here. So if we start to do this, feel free to throw your answers in chat, but I'll also start calculating here. If you don't have a calculator or phone by, we're going to add up all of the values and we're going to divide by 9. Okay, got some answers here. See if we're correct. Perfect, we are. So pretty simple here to add up all of the values. That's also what I got as well. So we are adding up all of the values and we're just dividing by the total number of values. So in this case, it is 9. Jumping to median. To calculate the median, you will first need to order your data set from smallest to largest. So the median will then be the middle value of that population. Another way to think about the median, it equally divides the data set into 2 halves. So a couple things to note. The median is not always a value in the data set. If you have an even number of observations, the median will be equal to the sum of the 2 middle values divided by 2. And the median is also less affected by outliers than the mean. So this makes it a more robust measure of central tendency in some applications. So looking at the values in the table below from the kidney disease and showing the packed cell volume for a sample of 9 patients, pretend this says patients and then packed cell volume here in our table. This was from our previous example. We didn't switch out these values here, but we have 9 patients and then this is their packed cell volume. So we want to first make sure that our data is ordered from the least to the greatest here. So from 22 to 54, it does look like it's ordered in that set. And now we want to determine the median value for the data in this sample. Can you guys figure out what the median value is in this sample here? Give a few moments. Okay, we see 45. Yep, so we're calculating the halfway point, which is actually our fifth patient. Since we have an odd number, we don't have to take the 2 and divide. So it will be 45. Okay. Final example here in this value is mode. So the last measure of central tendency, this is simply the value that occurs most frequently in a data set. Another way of looking at this is this mode represents the most common or popular value in your population. One thing to note, there could be an example of a unimodal data set, meaning that it contains a single mode. If 2 or more values were equal, the most common we would refer to in the data set as being multimodal. You can even have no mode if no value occurs more frequently than others. So again, this identifies a value that's most popular in our data set. Same example here. Which is our mode in this data set of 9 patients and their packed cell volume. And again, we don't have to have a mode, but I see our mode answer in the chat, thank you guys for responding, is 45 because it is actually the value that occurs the most frequently, with it occurring twice or with it having occurred twice. Okay. Great examples there. They're there to describe and give us some more flavor about the data set. We just looked at an individual descriptive statistic on an individual packed cell volume or an individual feature in our data set, but you can run those descriptive statistics on every single numeric value within your data set. And in our data set, we actually have quite a few numerical values. Another foundational topic we can touch on is statistical distribution. So this distribution is the shape of our data that it takes when it's plotted. Conventionally, histograms are most commonly used method for visualizing distributions. We actually already looked at a histogram on the first slide when explaining descriptive statistics. So the blue charts at the top of this slide illustrate some examples of simple histograms. These graphs measure the frequency or the proportion of observations that fall within a discrete range of values. These are ranges of values that are equal size to each other, and they're known as bins. On these plots, the blue rectangles represent different bins. So for example, the first bin in a given histogram may represent values from 0 to 100. The taller the blue bar is, the more frequently values occur in your data set, and that fall into that bin range. So one thing to note, the frequency measured by a histogram, typically plotted along the vertical y-axis, could be raw count values or relative percentage values, depending on your particular use case. So on this side, we have common distribution types and their associated histograms for reference. We have a uniform distribution. So this occurs when a data set values are evenly spread out across its range. And this is represented pretty flat. A unimodal distribution occurs when a data set values appears most frequently within a single range of values. This is represented by a histogram shaped with a single peak here. Bimodal occurs when a data set values appears most frequently within 2 different ranges, and this is represented by a histogram shaped with 2 peaks here. Your distribution can also be skewed. So you think of a skewed as a direction a distribution's tail goes in. So for example, a left or negatively skewed distribution occurs then when a data set's values are more heavily concentrated on the upper ranges of the population. This results in a histogram containing a single peak shifted towards the right hand or the left hand side, and the values trailing towards the left. And then right is the opposite, where the values are trailing towards the right. And then normal distribution is unimodal. It shows no skewed, and it's centered in the middle of the data set range. So we have our negatively skewed, a normal skew, or our unimodal, and then our positively skewed. So these are all descriptive statistics, once again, that describe almost the life cycle of your data. If we look at our example with packed cell volume, what type of distribution does this have? Does it have positive or negative skewed, uniform, bimodal, unimodal, normal distribution? Okay, I'm seeing a couple of answers here, all coming in as negatively skewed. Yeah, so it is a little bit negatively skewed. If we go back to kind of our descriptors here, negatively skewed where the it's kind of like trailing to the left here. And it has one peak kind of at 40 to 45. Even though there is like a few, it's not like truly just peaking here. There is a couple of points. We can see this is pretty negatively skewed from less than 15, kind of peaks around 40 to 45, and then trails again. Okay, so descriptive statistics focuses on the procedures and methods used to inform, organize, and summarize and present data. Now, they provide us a landing ground when we're looking at the descriptive statistics to make some inferences about the data. What inferences can be made about the packed cell volume data from the kidney disease table based on the distribution histogram shown at the right? So we saw it was a little bit negatively skewed. Now, when we're thinking of, putting on our investigative hats, what inferences can we start to ask from the data or infer from the data looking at this packed cell volume count? How it's, peaking around 40 to 45. Considering that this is a data set, that's looking at kidney disease, like who has kidney disease. Is there any, and there's no, right or wrong answer from this. Is there any inferences that we can start to ask from this data set now that we know the distribution of the packed cell volume? Give a few moments here to see if you guys have any ideas. Okay, let's see. Yeah, we have some probabilities. Maybe it increases with age. If your packed cell volume increases with age, I think that packed cell volume is the proportion of the blood volume that is occupied by red blood cells. I'm no health expert, but if it's centered around 40 or 45, then it consists of 40% red blood cells, which can be determined by age or can be influenced by age. I think 40 to 45 generally falls within the normal range for men and women and children. So we can start to look at maybe the majority of our data set is normal range of packed cell volume, and starting to think about, who in our data set has the kidney disease and what proportion of our data set falls within that. So some descriptive statistics that you can start inferring from your data. You don't have to wait till you jump to more advanced analytics to start learning about your data set and seeing what type of information and what questions you can ask from your data. Again, no wrong answers here as you start to investigate and ask questions of your data. So if we're looking to now understand the relationship between now two variables, we have our packed cell volume and we have hemoglobin. Is there anything that we can learn after looking at this plot? Our packed cell volume compared to hemoglobin. Yes, positive relationship, and they are highly correlated. So kind of jumping into our next topic here of correlation. The line goes up and to the right. They are positively linearly correlated. When we have higher hemoglobin, we also have a higher packed cell volume, which kind of makes sense from what packed cell volume is compared to what hemoglobin is. And we would expect the correlation coefficient to be actually close to 1 because they are tightly packed around this red line. So yep, they're positively correlated, which 2 or more measures are correlated when they have a mutual relationship or connection. So it can be positive or negative. When one increases or one decreases, the other one follows suit, the other variable here. So correlation essentially means relationship. There are many ways 2 variables can be correlated. Typically, when the word correlation is used in practice without any other adjective, it tactically means linear correlation. When 2 variables are visualized as a scatter plot, how closely does the graph resemble a straight line, which is linear correlation? And you can actually measure this in terms of a number, -1 to +1. And +1 would be perfectly linear correlated, and -1 would be perfectly negatively correlated, where they all of the data points sit perfectly on one line. So if you were to compare, packed cell volume to packed cell volume, comparing the 2 variables together, those would of course be perfectly positively correlated because they are the exact same variable. So you probably won't see a perfectly positive one or perfectly negative one correlated variable, but you would see something very close to 1 or something very close to -1 on this example. When you're starting to look for correlations, this can be great to jump into your more advanced analytics because you want to bring variables together that have a high correlation to one another, because that means your machine learning model can start to pick up on variables that are related to one another, starting to draw those relationships together in order to predict your target variable. So along with, positive correlations, you can also have many other different types of correlations. You can also do this on Excel as well. I know in previous classes that we looked at Excel and saw all of the great, descriptive statistics that Excel has to offer. So with Excel's core function, that's actually what we drew up this example with. And you can calculate the correlation coefficient. And as we probably predicted, it does have a very high positive correlation, pretty close to 1 at 0.9. When our hemoglobin starts to get in the higher ranges, 14 to 18, that's when we start to see some divergence in our packed cell volume. A note here, just because 2 variables are correlated does not mean they are caused, or they're caused by each other. So correlation does not imply causation, something to be wary of. In many cases, correlations exist because other variables that you're maybe not looking at are driving the relationship that are detected. So these are known as confounding variables. This is an example that is depictive of that. Here we have 2 things that are correlated with one another. Does that mean that they are caused by one another? We're looking at number of people who drowned by falling into a pool and correlated with films Nicolas Cage appeared in. So it's actually pretty positively correlated with 66%. So if we were to assume that these 2 things are caused by each other, that would mean every time, Nicolas Cage releases a film, then we need to add more lifeguards to a pool to ensure this doesn't happen, which is not the case. So these are spurious correlations. There's actually a lot of ones in the world that have it. I saw another correlation that was PhD degrees and in engineering, and the number of mozzarella cheese that was consumed over the year. And as more mozzarella cheese was consumed, more PhD degrees were received. Those two things are correlated with each other, but that does not mean they are caused by each other. So definitely be wary of that, but it is a good descriptive statistic to look at. So comparing statistics to machine learning is built off of statistics, and it is the core functionality of it, because machine learning, the upper limit of what it can do is what math can do. But the goals of it are a little bit different. So the goal of statistics explain relationships in our data set, where machine learning, we will actually want to take it a step further and make predictions on unseen data into the future. In statistics, we have strong assumptions about normality or linearity, but in machine learning, you can make fewer assumptions because your model is learning patterns that you can't necessarily detect or draw out from, which means it is a lot less interpretable. When statistics, you can draw up a high interpretation from it and point to exactly where it's drawing these relationships from. And bridging statistics to machine learning, we can think of statistics as the compass and machine learning as the engine. One helps guide and the other drives performance. The strongest data science solutions blend both worlds through feature engineering, model evaluation, bias and variance, uncertainty estimation, and explainability. These are all things that statistics are helping us leverage in the machine learning world. We'll use feature engineering in machine learning, but it is based off of statistics. Of course, we will evaluate our models, which is our next section, but it uses statistics and those formulas to help us. So they definitely are blended, which is why we just wanted to do a statistics primer before we jumped into our next section here, which is model metrics. Stop to see if there is any questions here, and we'll continue on to model metrics. So as a primer or review here, we have a couple of different types of machine learning. I'll briefly go over because it will help us determine what type of metrics we are going to look at today. So in general, we have two big buckets of machine learning, supervised and unsupervised, and the main difference between these two are, again, labels. If you have labels or you're choosing to use those labels, that will be a supervised machine learning model. So if you have a data set, we can think of a tabular data set like our kidney disease prediction. If you are, say, trying to predict which patients have kidney disease with all of the other variables in your data set, that will be supervised. Moreover, that will actually be classification because you're predicting a class. Does someone have kidney disease or do they not? It's a yes or no. That's classification. You're predicting a category of something that's qualitative. Versus regression, the other type of supervised machine learning, you are predicting a quantity. So say if we wanted to flip that prediction to, let's predict what the packed cell volume is, that's a number or a quantity, so that would be regression. We actually use two different types of machine learning metrics for classification versus regression. And then you have unsupervised, this is your other big category, and this is where your data set is not labeled or you're choosing not to use those labels. This is a bit more interpretive because your machine learning model will pick up on patterns to cluster or group things together. And from those groupings, then you as the data scientist or as the analyst will have to draw up why these clusters or groupings are forming from your data. It will not be told to you by the machine learning model why certain data points are grouped together. Okay, so jumping in before we get right into model metrics, we'll give an overview on how we're going to get to those metrics by how machine learning is working. So in a machine learning problem, you'll have 100% of your data set. So back to our kidney disease example, we have many lines, and those are all different patients with all of their different features and variables that we have that we looked at the data dictionary at. The normal train test split is 80-20. So this means we take 80% of our data set, the majority of it, and we'll use that to actually train the model. We'll feed that in to the model, and our model will then learn about the data and how it's related to the target variable, and it will create this trained model. We reserve 20% of it for our evaluation or our model metrics to be applied. So we can actually use our trained machine learning model, apply it to our testing data set, and evaluate it to see if it's up to the thresholds that we've previously defined, or if we need to go back and retrain it. So this is a diagram of that. We have 100% of our data, 80% is split into our training, 20% is split into our testing. We will feed that into our chosen machine learning algorithm model, whether that's classification or regression. We'll get our trained model that we then apply to our testing data. It will provide us a prediction, a class, or a number. So now we have our prediction, and we can compare it to our actuals of our testing data set, so we can validate that model. It is a very iterative process. It's very unlikely that the first time you train your machine learning algorithm, that will be the model that goes into production or deployment. You'll probably need to go back and retrain it, and this means picking a different model, refining the parameters of that model, gathering more data, adding additional features. The list goes on, but you'll choose additional steps you want to take, retrain that model, and it's kind of this iterative process until you get validation metrics that are up to performance. While your model is training, it is ultimately trying to arrive at a global or a local minimum. So it is going to train these parameters so it gets as close to the target variable as possible while minimizing loss. We can measure our performance with a couple of different data sets here, or a couple of different ways. So measuring a model's performance is important for users to be able to trust the model's outputs, especially against a tracked threshold. This threshold will be different depending on your specific use case. Essentially, how important is it that your model is getting something right? Models' performances are tracked over time, and they can have a direct and indirect adverse effects. So for classification, we'll use a set of accuracy, precision, and recall, the main ones that we'll be focusing on. And if we're choosing a regression problem or a numeric prediction, we'll be looking at mean absolute error, mean squared error, root mean squared error, and R-squared score. Okay. So for classification, accuracy, precision, and recall are going to be used for our metrics. And we can explain some of the math behind. So statistics backs all of these equations up. In many cases, there is obviously formulas that go with these. You don't necessarily need to memorize these formulas when implementation. If you're using something like a programming language like Python, those will have functions that are stored within the libraries that you can call, so you don't actually have to write out equations like this. The important part of this is not to really memorize the math, but just to look at these concepts here. So accuracy is a measure of how often a model gets a prediction right. It can be misleading, we'll look at on the next slide, especially when we have an imbalanced data set, which is actually pretty common that you'll be looking at an imbalanced data set. So we'll look at why accuracy can be misleading. So then we lean on precision and recall, which are a little bit more precise in measuring the actual accuracy of your individual classes. So we can look at this example first. So this is our imbalanced data set. So say if we were just measuring accuracy, and that's really all we cared about is how accurate can we get this model. If we had a class, and we can go back to this kidney disease, if the majority of our patients did not have kidney disease, around 94%, and around 6% of our patients in our data set had kidney disease. If I cared about accuracy, and every time I predicted that my patient did not have kidney disease, I would be right 94% of the time, which is a great accuracy. But is it really? When you're looking at precision and recall in this individual use case, what we actually care about more is predicting that 6% of the time. How often are we getting that 6% correct? that is where we lean more on precision and recall to explain that story. So we actually have, let's see, an interactive, and I can put this in the chat too, that explains precision and recall really well. And it looks at imbalanced data, and you can actually move these bars here to demonstrate. So if we have, this is for a cancer classifier, so it uses accuracy just uses the classification threshold of 0.5 in general. I actually moved it from where it originally was. So a 0.5. So if we classify patients with probabilities greater than 50% to be cancer positive, otherwise they would be cancer free. This is a common threshold for many of our models with output probabilities. When it has the intuitive effect of assigning values to be positive when the model determines that they are more than 50% likely to be positive. But you can actually move that threshold here and see how it affects your model accuracy. We also, in our formulas, look at our actual positive and our predicted positive and our predictive negative. And these are our true positives, false positives, true negatives, and false negatives. So this is the formula for accuracy, precision, and recall. You're looking at true positives, which is the number of positive instances correctly classified. So someone does have cancer and you predicted them to have cancer. False positives, the number of negative instances incorrectly classified as positive. So you predicted someone to have cancer, but they do not have cancer, a false positive. A true negative, the number of negative instances correctly classified as negative. And then false negatives, the number of positive instances incorrectly classified as negative. So that all of those four variables are then used in the accuracy equation and then our precision and recall. So here they list the big problem with accuracy is when you have imbalanced data set, which is almost every data set where you don't necessarily want to rely on accuracy. So instead we go to precision. So precision is the ratio of correctly predicted positive classes to all of the items predicted to be positive. So how precise are you when you predict someone to have cancer that they actually do have cancer? So the true positives over the true positives plus all of the false positives. So this intuitively tells us how correct or precise our model's predictions, positive predictions are. So we can try to move the threshold here to see how precision worsens when the increase of false positives happens. So this is a threshold here that you can start to define, how precise that you want to be. In this case, when you are less precise, you will bring in more false positives where you are predicting someone to have cancer and they don't. You are getting some of those positive predictions here. So these are the plus, the little pink icons here, the pink circles. Those patients actually do have cancer, but you also are getting more patients that don't have cancer that you are predicting to have cancer when you lower that threshold. And then finally, recall. This is related metric to precision, but recall is the ratio of correct positive predicted classes to all of the items that are actually positive. So instead of the false positives on the denominator, you are adding the false negatives. So it measures of the actual positive instances if we were able to correctly predict or recall them. So looking at all of the positives, how many of them are you gathering? So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8 that we're trying to predict correctly. And then our recall metric will be how many of them that are we trying to predict correctly, or how many of them did we predict correctly. So there is a trade-off. You may care more about recall versus precision in specific use cases. So figuring out which one that you want to identify. Of course, we would love, 100% accuracy or 100% precision and recall. But we sometimes have to make a decision what we care most about. And you can actually fine tune your model to care more about precision or more about recall. That is a similar conversation, when we go to regression metrics, you can also identify your model to care more about mean absolute error or R-squared, or when you're actually training your model. When we look at regression metrics, there are 4 different common metrics that are largely related to each other, but give slightly different insight. So when we're looking at mean absolute error, you maybe could tell from the name that it actually takes a positive difference, or the absolute value, between each prediction and the actual value. So when we have regression, again, we're predicting a number. Here we can consider our X and Y axis. Along this dotted line, these are our predictions. These are where, our machine learning model is predicting for each point of where it will fall. And these dots that are scattered along it, these are our actuals. So now we're comparing our actuals compared to the number of our predicted. And that difference here is called a residual, or our error. So ultimately, of course, we'd love our dots to be very close or on our predicted values, meaning that we have, a high accuracy. But here's how we measure that compared to our classification. So for our mean absolute error, it takes our predicted minus our actual, and it takes the absolute difference. When we compare that to our mean squared error, it's the same formula, but it's actually squaring those residuals. So therefore, it will penalize the larger errors more severely because it does square it. So if you have your predicted value to be 10 and your actual value is 1, that's a 9 of our mean absolute error. But when you square it, it then becomes 81. So it really intensifies. If you have strong outliers at a certain point, your mean squared error is going to indicate that. Your root mean squared error is the same formula as mean squared error, but you are square rooting that. So it measures the standard deviation of those residuals. And then finally, your R-squared score. I think this is most common, where you see the coefficient of determination representing the proportion of the variance in the dependent variable. Your R-squared score is essentially the coefficient of how well your line is fit to your data. A high R-squared score, really close to 1, means it's perfectly fit. If it's 1 exactly, that means every time you predict a point, it actually is that number. So you want it to be very close to 1, obviously, but you don't want it to be exactly 1, because that would be a case of overfitting. When we look at overfitting or underfitting, it may be tempting to have models that are 100% accurate, or have a 1 R-squared score on your training data set. Although it seems ideal, it's not actually what is desired in practice, because real-world data is always comprised of 2 components. One, there's an underlying ground truth that connects your input and output variables in a predictable way, and random fluctuations that cannot be directly measured in most practical applications. Because any model that you build will not only be subjected to real patterns within the data, but also random fluctuations that are impossible to account for when collecting your data. So when you're building out a model, you want it to be flexible to future. In theory, you're going to take this model and you're going to deploy it to the real world. You're going to predict on data that it's never seen before. So if it's 100% accurate to the data that's been trained on, it can't really fit well to outside scenarios, and you'll see a vast drop off in accuracy after the training testing life cycle. May seem counterintuitive at first, but the models that perform best on testing data in the real world are often not the ones that exhibit great accuracy on the training data. This is another descriptive example here to explain overfitting from another point of view. So if you ask someone, make me a bed, and they checked my sample of sleeping positions a few times during the night, maybe they would want to create a mattress that perfectly fits me, and so it would look like this. However, this is actually not my ideal bed because it takes into account, one sleeping position, maybe my most common sleeping position, but it's not adaptable to maybe the other positions that I would see throughout the night. So the same follows suit. when you're looking at your data as well. You want it to be adaptable, good fit for what your data looks like currently, but also adaptable to what the data can look like in the future. And I'm going to pause for questions and a break here. So I'm going to give us actually a 5-minute break, and I will bring us back here at 11:56. And I will pause to see if there's any questions, and afterwards we'll start jumping into neural networks and their applications. Let me know if there's any questions, though, in the meantime.
Feel free to put comments in the chat.
Erica, looks like there is one question in the chat.
Yes, I see that. I didn't know if I was typing out an answer actually right now, but I don't.
Okay.
Yep, but I can type it out and also talk through it. So root mean squared error does penalize large residuals more so than the mean absolute error, because you are squaring the errors and then you're taking the square root. You would want to use mean absolute error because there is a linear error penalty, and it provides more interpretability. So it's easier to explain because you could say, like, on average, here is our residual rate or our error rate versus the root mean squared error, because with root mean squared error, you are taking that square root. Root mean squared error, it will penalize the large errors more. So the large residuals still have a bigger impact, but it's better for like normally distributed errors. So if your residuals are like normally distributed or have the standard deviation of the residuals are Gaussian, then root mean squared error would be better for you. And then many machine learning models prefer root mean squared error because there's a nonlinear component in many data sets. So mean absolute error, great for linear, versus root mean squared error is great for nonlinear. And it's more sensitive to model performance. So if you care more about like punishing larger errors, you would still use root mean squared error. If you're working with normally distributed, you would still use root mean squared error. And I can write this out too as well. Okay. So I was continuing to write this out, but I will treats. Okay. Okay. Perfect. So our break of today, and then we will move to neural networks and their applications. Okay, so there's nothing really new under the hood in terms of machine learning from what we've previously learned with deep learning, but the amount of data increases. As the amount of data increases, the older machine learning models tend to plateau. So that's where really where deep learning comes in. And deep learning algorithms shine because you have more data, and we also have the computational power to increase performance, which empowers a lot of breakthroughs that we've recently seen in things like large language models. There's also a trade-off. You have higher performance, but you also lose more explainability and interpretability as you get into deep learning models. Ian Goodfellow, one of the forward thinkers of deep learning, he's a computer scientist and also an author. He has stated that a hierarchy of concepts allows the computer to learn complicated concepts by building them out of simpler ones. So we're not going to make you an expert in all the way things are structured, but want to provide a high-level overview of the simple components and how they are connected to get a powerful model. So we start at the lowest level of data, we link pieces together at various levels to learn complicated concepts and phenomenon. Let's get into deep learning. So this is the idea behind deep learning. The engineering principle is biomimicry. So we look to nature to help us solve engineering problems. So deep learning is partly inspired from biology, kind of like we call deep learning networks neural networks. The architecture of this model has many similarities to the human brain. Our brain has a collection of cells that receive information from your senses, and each cell has a job for processing a specific piece of info that you're receiving. That info comes into that node processes the info, and then your cells are linked together and shares all of the processed info. And by sharing that info, you get that human mind. We have interconnected neurons that feed one another, and individual neurons can fire for activated tasks. So neural networks are the digital version of our human brain. We similarly have a collection of nodes in our neural network. It takes inputs, it processes it, and it shares it with the other nodes that it's connected to make that final prediction or assumption about the input that it's being received. So to explain this architecture a bit better, this is our most basic network. It's called our feed-forward neural network. And all of the other neural networks we'll look at today are built off of this one. So similar to kind of the network that we saw previously from our brain, we have a collection of inputs. They're taking together, they're processing it to make this output. So each of these inputs are what we call nodes. And these are broken, whatever the input is, whether it's an image or a tabular format, that is taken and put into each of these nodes. We combine those with what we call edges. Those are these black lines, and we can think of an edge like a mathematical equation. It's performing some type of it's performing something on that node, like addition or subtraction, to create a layer. So once that computation is performed on that input, combined with that edge or that computation, we get a layer. You can do this many times and actually build up these layers. And the deeper or the more layers that you have, the deeper your network becomes, hence the name deep learning. Then you'll provide another edge or computation to get your final output layer or your prediction. So our goal in the training process is to optimize all of these weights so that we can get a great prediction or a great output. What's great about neural networks and why we use it is because it does allow for increasing complexity. So if you have your basic linear regression line, you can think of y equals mx plus b. You have two parameters you can choose from. In our linear regression, you have the height of the line and you have your slope of the line. These are your two thetas, your theta naught and your theta 1. You can control it to meet and match what the data looks like to a certain extent. But if your data is not, linear in nature, then this equation would not be great for you. You would never get a great R-squared score or a line of best fit because there's only two parameters that you can choose from. You could do multiple linear regression and kind of do it on a planar field where you have multiple inputs to one predicted output using several parameters, but it is still very linear in nature. But when we go to neural networks, this allows multiple inputs to multiple outputs using many model parameters. So if your data is not linear in nature, you have a lot of it, there's a lot of complex relationships to draw from, that is where your neural network comes into play because it allows for that increasing complexity to be understood. Building off of our feed-forward neural network, the first one we want to touch on is convolutional neural networks. Convolutional neural network is a further advancement of our feed-forward neural network. What's different about this one is there's additional layer that's passed through. It's called a convolutional operation to help identify important visual elements in an image. So it's great for image data or for video data, and it can help you with things like image recognition, image classification, object detection, facial recognition, and image segmentation. So I think of classification. Here we have an image of a cat, and our convolutional neural network is going to say this is a cat, or we can localize it and bound it in a box and say the cat is within this box, or detect multiple objects, or instance segment and actually cut out where in the image or the video feed this particular object is. I like to think of like a self-driving car. If you've ever been in a Tesla before or self-driving car, you can actually see how it is or where it's segmenting the instances or the specific objects around you. If there is a motorcycle passing you versus a semi-truck, it will actually depict exactly what object and how big in size it is. Is it a tree? Is it a person? Is it a bike? Because it's actually classifying what it is, and it's actually segmenting where it is because it has to be very precise, obviously, in the objects around it. So convolutional neural network is deployed. In contrast to our brain, computers can only understand numbers. So even in a convolutional neural network, we have an image, we'll ultimately convert that to a matrix of numbers. Each pixel will be broken up and will be fed into a convolutional neural network as a series of numbers, and that will be the pixels essentially of our image. The convolutional operation will actually sweep through our image and will create a feature map. So these layers will be built up. It will first look at the lower level layers, like light versus dark. And then as our convolutional operation starts passing through our image and every pixel, it will start to build up, higher level features like where the lines begin, what colors are in the image, and start to bring together the feature map of our entire image. And we can actually use that feature map to predict what we think that image is, or where in that image our object is. So it's very common to put a feed-forward neural network to do that classification for us on top of our convolutional operation. So here we have, the input image, say, of our cat. We can stick our convolutional layers on to our input image, and this will start building up that feature map, or it's essentially a matrix of another set of numbers that will indicate, what that image is and what those features are within that image. And then we can attach a feed-forward neural network at the end to then do that basic classification for us. Is it a cat, dog, horse, and where that image is. So our next neural network is called a recurrent neural network. And this is great for data in series, things like stock prices or language data. Again, this is a modification of a feed-forward neural network because it uses a feedback mechanism. Recurrent neural networks, or RNNs, have an additional input, which gives the output of the previous step in the computation a memory. So it's best suited for this data in series because it knows what happens in previous steps. Long, short-term memories is what gives this recurrent neural network our memory. This is the key component of recurrent neural networks because it helps remember all the previous steps. So in this graphic here, we can see why it's great for data in series like language data. This is great for natural language processing because it gives the previous or gives the current output the previous output's response. So if we were to ask it for, say, the next word prediction, and we were just to say, what comes after the, and that's all it had, our output, our prediction may be all over the place. It could say anything under the sun that comes after the word the. So we wouldn't get a very accurate prediction. But because we're using a recurrent neural network, we've trained it on human language, on the English language, and we can feed in this entire sentence. So now instead of just saying what comes next, what comes after the, we know the whole sentence. The plane flew over the. Now what comes next? So it has all of those components that previously came forward or that previously came. So now we can understand and predict, okay, now it maybe flew over the mountain or the world or the country, and something that's more logical that fits in this sentence. We actually see this deployed in your phones too. If you're typing on your phone, at the bottom, there is that next word prediction that comes up pretty frequently. And if you have ever realized it or noticed it before, as you're typing, those words change. As you're building out that sentence, it understands your sentence, and those words are logical to what you're typing out. It's probably not the word that you are trying to type out, but it makes sense in the context of that sentence, and it actually is learning your language every time you use it to give you words that you are likely to select. So recurrent neural networks are widely used for text and speech applications, things like that next word prediction or translation, speech to text and text to speech, sentiment analysis, and summarization. A lot of things that we use in the natural language processing world to process natural language. And recurrent neural networks are the baby sister to what we're seeing in transformer learning. Transformer learning diverges from our traditional feed-forward mechanisms and embraces a self-attention mechanism to efficiently process input sequences. Many modern large language models that we're seeing today use this transformer architecture. So this is relatively new. It was transformer architecture was first introduced in the paper Attention is All You Need in 2017. And this has really revolutionized natural language processing by employing these self-attention mechanisms. We'll look at self-attention mechanisms, but they are they allow transformers to weigh the importance of the different parts of the input data independently. So unlike our traditional recurrent neural networks and the long short-term memory that they have, transformers can process entire sequences of data simultaneously, which makes it a lot quicker for, say, training on the entire history of the internet, something that we've seen ChatGPT in the GPT transformer model that was recently released in 2020 do, because it was employing this transformer learning, something that would have previously taken a very, very long time can now be done relatively quick with transformer learning because it can process input sequences in parallel. Transformers also allow for billions or trillions of parameters. Each of these parameters are, you can think of that like y equals mx plus b. We have our y and we have our b, or we have our m and we have our b, our slope of our line and our height of our line. Those are the two things that we could have changed, and those are two parameters. Now transformers are made up of billions of parameters. I think GPT-3, which is one of the first models that OpenAI came out with, and ChatGPT has 175 billion parameters, which makes it great for natural language because we have we have a lot of nuances and like niche within human language. And so transformer learning can start to pick up on all of those nuances within our language to start efficiently training and becoming something like a chatbot. There's also several other applications of deploying large language models to different and various different data sets. Apart from your chatbot, you can actually apply it to tabular data sets and fine-tune it for your own purposes. Transformers are great for natural language tasks like machine translation, text summarization, and language modeling, things that we have seen recurrent neural networks do, except they're just the latest and greatest. They've also been adapted to other domains like computer vision and audio processing. So this is the self-attention mechanism. So they allow the transformer network to weigh the importance of different parts of the input data independently. And it can process entire sequences simultaneously, making them much more faster and more efficient. So when we see it starting to weigh the importance of different parts of the input data, great for language data because now we feed in the sentence, I gave my dog Charlie some food. And instead of just taking the sentence at face value, it's starting to weigh the inputs separately. Who gave? Why did they give? What did they give? And it's starting to measure and actually weigh this using the self-attention mechanism of what are the important pieces in this sentence and how are they related to one another. This is the transformer architecture. So transformers, they're well suited for machine translation, text summarization, language modeling, and this is that the parallel processing here that transformers deploy. You don't have to understand this, but essentially this is much more complicated than our other neural networks that we looked at, where instead it's deploying many neural networks all at the same time, so it can take in a lot of data all at once. So we've seen revolutionized large language models. I know ChatGPT is a common one, but there's also things like Microsoft Copilot. There's the Llama model from Meta, and we also have several other commercial companies releasing their own versions of large language models. And they're actually continuously improving because as we are generating more data, we are retraining it and retuning those parameters to become more natural to the human language. we have time here at the end, we'll also show an example, a co-pilot example for using transformer architecture and helping out with processing our data for us and giving like a starting script. Transformers are great for helping programmers kind of start up their process. And then the last network we'll touch on today is generative adversarial. So generative adversarial networks, they are different because they consist of two different networks that are competing against each other. They'll have a generator and a discriminator. GANs can generate new data instances that resemble the data set. So they're actually generating data that is supposed to look as much like the real data as possible, so that the discriminator cannot discriminate what is real versus what is fake. So there's a couple additional training steps, depending on what you're mainly focused on, the generator or the discriminator. You're training the discriminator to distinguish between what's real versus what's fake. All the while, the generator is trying to trick the discriminator and create data that looks as much like the real data as possible. So this is what that output looks like. You have your real data that's being fed into the discriminator, along with the generated data that is understanding and learning about the real data, taking that as inputs and generating its own data. And then you're trying to discriminate what's real or what's fake. If I cared more about the generated or the generator, I would really want to make sure that my discriminator cannot distinguish between what's real or what's fake. And then I would have data that looks so real that you can do things with it. So there's definitely useful applications for this. So you can transform your data in useful ways. Text to image generation, we've actually seen large language models deploy this. So that you can ask ChatGPT now, can you make me an image that looks like, and there's also other transformer models that are using this. Face aging, generating realistic photographs, photograph editing, semantic segmentation, 3D object generation, or video prediction. So this is actually generated here by a generative adversarial network, and you can actually generate this image. So as you can see, a lot of GANs are not great with words, I've noticed here. So you can see generative adversarial not work. It almost got it right, but it's not great with words for some reason, generating those. But here, this is just kind of a depiction of that, where it's like a counterfeit artist. I'm trying to make artwork that looks exactly like the real artwork and trying to fool the discriminator or the art critic. And the art critic, oh, no, this is not real. So then I'm going to go back and I'm going to try to create another image that looks even more like the real artist's painting. So therefore I can fool the discriminator or the art critic here. And GANs are very helpful, especially in today's day and age, because we can generate data. So it doesn't actually have to be image data, but we can use GANs in tabular data sets, especially with transformers in action. Transformers are pulling in so much data that there's almost a data shortage in a way. Even though we have data being generated every day at a vast amount, our transformers are able to pull that in and train on it. So we are starting to, ask ourselves, is there any more data that we haven't trained on already that we can pull in? And if there's not, we can actually deploy GANs to create more data that looks very much like our real data, but it just gives more opportunity for our neural networks to learn, to adapt, to adjust, and to become more precise. So there's definitely a lot of useful applications in GANs, especially just, at a smaller scale. Say you didn't have enough data in your own project and you wanted to create more synthetic data. So your machine learning model has a higher chance of learning, what that subset looks like. That's on a smaller scale. But there's obviously adversarial purposes here. So generative adversarial networks. What are some potential consequences of GANs with respect to security? And I'm going to think of this as like health security. Normally, obviously, I brief this to the Navy and to NAVWAR. So there's like national security consequences, but maybe with respect to the health field. Is there any consequences that you can think of when working with health data and how GANs could have an impact on that? I have a few ideas, but would love to see if you guys have any ideas here. I'll give a few moments for you guys to put your answers in chat. Again, no particular right or wrong answer, just thinking if we were generating fake data and it looked a lot like real data, could there be any consequences in using that in our health field? Okay, introducing nefarious bias on purpose, maybe, or you are creating synthetic data that looks maybe too much like a nefarious actor, and then that is skewing your model results. Love that answer. Any other answers we have? I have a few. Keep thinking about reinforced health related disparities. Yeah, especially I think we've seen a lot in, we've come a long way, but in chatbots or in facial recognitions, if it's not like trained or in health related disparities, there's such a small subset of something and we're training it on that, like we are talking about accuracy, if it doesn't have enough chance to learn on that specific subset, then it can become a bias down the road, create disinformation like vaccines are cause of autism. Data used for training is sensitive. Okay, all great answers here. Some that I thought of here, which are very much in line with what you have also suggested, are manipulating clinical data so they could realistically create entirely synthetic clinical trial results or fake patient records. So this could corrupt peer-reviewed literature. It could mislead downstream research. It could cause harmful health policy or drug approval decisions. I think all of you guys have, or some of you guys have mentioned that. There also is a risk for privacy erosion or re-identification risks. So although they're used to generate synthetic patient data for research, poorly designed GANs might lead to identifiable real patient features, because in order to create a GAN, you have to feed in real data so it can learn about that. So this could raise HIPAA concerns, and adversaries could reverse engineer patient level data from models trained on this sensitive information. So even though we're calling it synthetic data, does that mean it's now public or releasable information? It could also lead to the erosion of trust in biomedical institutions. So there's a very similar DoD context where if you fake an image and it's found out to be fake, you're now eroding trust. So you could fake clinical images, studies, or trials. It could become widespread, and then public institutions could erode, or trust in public institutions could erode. So imagine like a deep fake of a government doctor falsely promoting a drug, or a fake leaked NIH study pushing disinformation around public health. There could be legal and regulatory challenges. So the regulatory bodies may struggle to keep up with the pace of synthetic data generations. Questions also arise about authorship, attribution, liability, and consent when synthetic data is used in published studies. So lots of adversarial purposes here, generated fake medical images, manipulated clinical data, privacy erosion, erosion of trust, and then this legal and regulatory challenges. Like all of machine learning, AI, deep learning, there is great purposes and use cases that we can use it for, because it is really pushing the boundary of what we previously understood, and now what we can do with all of this data that we have access to that we previously didn't have enough compute power or the technology to access this and really make some impact or insights on our data set. But now there's also, of course, adversarial purposes, which is really why at the root of all of our machine learning work we are trying to build out responsible AI solutions and have that responsible kind of be the key component of it. How can it be trusted? And questions to ask yourself and to ask of the AI model. How was it created? What data was used? How was it manipulated? How can the results be trusted? Outside of obviously generative adversarial networks, there is questions that you should ask of all AI capabilities to make sure that this can be trusted, especially when deployed in the real world, and actions are being taken from those predictions. Okay. So in review, we have 5 minutes left here. We have our day 2 summary. So here we covered statistics primer, model metrics, and our neural network overview. This was not to make you an expert in any one of these fields, yet introduce kind of this wide field of machine learning, of deep learning, and how we can start to access that through different applications. I want to poll for questions. And before we get to questions, we will also, I think, have a survey in the chat. Anya, let me know if you want to come off mute and say anything about this, but we also have an upcoming webinar at the last Thursday of next month for fair and AI-ready data sharing. You can scan this QR code to register for that from 2 to 3 p.m. on May 29th. And then I also think we have a survey, if I'm not mistaken. Oh, yep, just popped up on our screen here. So we'll take the last couple of minutes. Let me know if there's questions. You can always type in the chat as well, but there is a survey in the chat. Would love if you could answer this so they can continue to build out webinars that you're interested in with topics that you're interested in. I'll give a few moments here before the end of the class for any questions and for the poll results to come in. Yeah, so question here. So in the first hour, you described a number of statistical procedures. When do they start becoming calling machine learning? So those basic statistics, I would use in every machine learning project that I'm working on in the first 4 steps. If you remember the data science process, problem statement, data acquisition, exploratory data analysis, and data prep, those are all used in those steps to acquire, to prep, to analyze your data before you're jumping into anything like modeling. When it starts to become machine learning is when you deploy a machine learning model to start making predictions. So statistics describe your data while machine learning attempts to predict on your data. They're very intertwined though, because even your most complicated machine learning algorithms is just a series of math equations. So understanding one will lead you to understanding the other, but that's the jump. You're describing your data or you're jumping to predict on your data. That's kind of the distinguishing feature. Do these techniques work on both structured and unstructured data sets? Yes, to an extent they do. Structured data sets, your computer likes more, and you can do a lot more with, but there is a lot of techniques to work with unstructured data sets and turn them into structured data sets. So something like images, unstructured, but there's techniques you can deploy to make them a structured format, and similar with, non-image data, if you have sensor data, you can turn that into a structured format to start using the full potential of your machine learning capabilities. Thank you guys for your questions. Yeah, so statistical methods have been doing predictions for the last 80 years, regression and classification. Yeah, so we looked at the increasing complexity of predictions, like your line of best fit on Excel. I guess you could call that a descriptive technique. If you remember the image, if you were in the first class for data science processes, we had that image of the crack in the wall, and you call that statistics. It's always been there. It will always be there, but when you frame it and you put it in a certain light, you can call it machine learning. And if you call it artificial intelligence, everyone starts to show up and look at it and care about it. But if you really digest what's in that, what is that crack in the wall? It is statistics. It's been there forever. Now our technology has gotten to a point where we can build on that and start to draw more patterns and inferences that we had before. But if you want to go back to the beginning of time, your basic statistics, your line of best fit can use for prediction, this linear prediction. But now you can look at nonlinear data sets. You can look at data far into the future and understand those parameters a bit more. But if you're going simple, for the simple understanding and the basic understanding, statistics describe your data set, machine learning predicts on your data set. Oh, thanks for joining from Italy. I don't know what the time difference is there, but I'm assuming it's nighttime. Thank you guys.